Hey, hello everyone. This is going to be chapter 9, a continuation from our last chapter. This is called Further Reactions of Alcohols and Chemistry of Ethers. So in the last video, you learned how to synthesize ethers, these ROR compounds. You can either do it through SN1 or SN2 ways. Um, and they have very specific chemistry. Under the presence of acids, they cleave into their respective alcohols. That's how you can tell which one will be it. And they're just really fun to work with. They can be used as protecting groups if you want to do Grignards and stuff like that. So here we have a form of ethers, which are called cyclic ethers, right? So I want you to notice the difference here. This Na is guarding this oxygen's negative charge. So there's an implicit negative charge on this oxygen, right? And then in this molecule, we have a good leaving group and a primary carbon. So what this is going to do is it's going to attack the carbon that has a leaving group and go there, and it's going to form a 1, 2, 3, three-membered ring, right? Like that. And then this is now NABR, right? So I want you to go back. You're thinking, why is this stable? And like, why are these cyclic compounds stable? It's because of this chemistry with this oxygen here. Despite the fact that they're not at 109.5, this oxygen makes it so that they're somewhat stable. But these epoxides, these are what it's called, cyclic ethers are also known as epoxides. They actually form really readily, especially in this three-membered carbon. These epoxides form very readily, right? So we can do the same thing for however many amount of carbon chains that we have. So this is going to be 1, 2, 3, 4. So it's going to be a 4 carbon chain, right? Or a 3 carbon chain with the ether right there. Oop, that is very ugly. Right there, right? And then it's also going to add NABR. So actually, we see that this compound over here is faster in forming than this compound. The reason why is if you look at the relative distance between the two carbons, between these two molecules, the distance that this oxygen has to travel, it's shorter for this upper oxygen because it's only 2 carbons away versus 3 carbons away, right? And you'll actually see this where these three-membered epoxide rings are actually more favored and more stable. So it's going to form faster and it's going to be even better than this 4-membered. So most of the epoxides that you'll see will be in the form of this triangle with an oxygen on the top, okay? So let's learn how to make epoxides now. I just showed you all how to make it over here, but we can use an alcohol that is 1 carbon away, right? This carbon has the alcohol, and then 1 carbon away from it is a good leaving group. If we use a strong base, it's going to deprotonate this hydrogen, or if we use a sodium metal, it's going to go up top like this, or we can even use potassium to make this a okay, right? So we just want to deprotonate this H and make this oxygen a good nucleophile by having it with a negative charge, like up top right here. And if it does that, it's going to attack in an SN2 way right there, and it goes back out, right? SN2 fashion. Okay. And because it's SN2, we do have to worry about stereochemistry, right? So let's take a look at this compound right here. That carbon is a chiral carbon. So let's see what it is. It's 1, 2, 3, and then this implicit hydrogen is a 4 here. It goes this way, so it's S, right? And then what happens when we have it here? This is now 1, and then this is now 2, and then 3, and then this implicit hydrogen here, which is now going this way, which is clockwise, so it's R. So it's going to flip the stereochemistry because it's going to be in an SN2 fashion, right? So you do have to worry about stereochemistry there. Just be careful about that with these epoxides, okay? Or with the formation of epoxides. So next up is this concept of an SN2 way, right? Like I previously said, this is an SN2 reaction. So do you think that once we're treating it under this butoxide base, right, it's gonna grab this hydrogen up here, it's gonna turn this O um, into a good nucleophile. So let me just show that real quick. It's gonna look something like this BR, and then this BR as well. So now our problem is we have two possible leaving groups, but like I said, and I'm going to keep saying this, it's going to be SN2. So SN2 would much prefer the backside, right? So because of that, it's actually going to attack it on this carbon over here, right? So because the backside of this carbon will be the front. So sorry about that. My computer died. But yeah, let's get back. So we were talking about SN2 reactions with epoxides, right? And I said once this base takes off this acidic hydrogen, it's going to turn this into a good nucleophile, right? And then now we have two carbons here that we can, two carbons with two leaving groups that we can attack. We can either attack this Br that's on a wedge, or we can either attack this Br that's on a dash. SN2 reactions happen backside. So I want you to think opposite here, right? If my O is on it's on a wedge, and this BR leaving group is on a dash, we're technically, even though this dash is showing you that it's in the back, we're technically attacking it from the opposite side, right? Remember, SN2 reactions are basically attacking it from the opposite side, which is why we call it the back side. Because now, if I attack this bromine here, I'm on a wedge and this bromine is on a wedge, so we're going to attack from the same side, right? And you know SN2 reactions don't occur that way. So this is why we attack it on this bromine, because even though this is pointing in the back, technically we're still attacking it from the opposite side, which has less steric hindrance, right? So once that happens, this bromine will leave, and then now that oxygen is on a wedge. So now our compound will also be on a wedge, right? It's gonna look like that with this bromine up top right here on this side right there, sorry. Okay, so that is going to be our compound. And then now, let's learn about their chemistry. So what can we use them for, right? So here we have an epoxide with two methyl groups. This is an ethyl group, right? Because this is one carbon and then one carbon here, and then the methyl group. And then we have it under this reactant, which is a Grignard, right? And Grignards are good nucleophiles, but they're also in acidic conditions. And in acidic conditions, attacks happen SN2. Okay? So we have two carbons here that aren't even, right? This carbon is not the same as this carbon because this carbon has more groups on it, but this one doesn't. So if it wants to happen in an SN2 fashion, it's going to attack the less hindered side, right? You can see how this is the less hindered side because, well, this one has three carbons attached to it. Um, it's a tertiary carbon, right? 1, 2, 3, versus a secondary. Well, this is a primary carbon. So this is going to happen in an SN2 fashion. So what do I mean by that? This ring is going to open up. This carbon is going to attack it over there. And if that attacks over there, then this ring has to open up to that oxygen. And then look at what we formed. I find this way to be the easiest way of visualizing this. I just want to imagine this bond here gone. This bond is no longer there. So what happens if it attacks it from there? We still have this bond over here with this and this, right? And then now we have this bottom layer of carbon. So let's draw that here. This bond here, C to O, is no longer, but we just made a C to C, right? So we have this. You see how that sort of opens up now? And then don't forget, we still have this negative. And then if we do an acidic workup, right? You can do an acid workup. You will get a alcohol, right? So as you can see, it's going to attack it from the less hindered side because this is an SN2 type reaction. And when that happens, it's going to lose this bond here, this C to O bond, because that C to O bond went over to the oxygen. And if you do an extra acid workup, you will get a alcohol here. But it adds on to this carbon because it's in basic or nucleophilic additions, and this happens for every nucleophile or base that you will see. Okay, and then now let's see epoxide in acidic conditions. Here we have an acid, right? HCl, hydrochloric acid, and then again we have the same compound here. So if you can sort of tell with the pattern, in acidic conditions, it's going to attack the more hindered carbon. So let's see how that happens. We have a huge delta positive here and a huge delta negative there. This oxygen has lone pairs, so we're gonna attach one of the attack one of the H, and we get this. If we do a quick formal charge, this oxygen has a +1 formal charge. And let's think why it happens on the more hindered side, right? So this carbon is a tertiary carbon versus a primary carbon. Because this oxygen has a positive charge, it's going to be pulling electron density away from these carbons, right? And which carbon is going to contribute more to that pulling? This tertiary carbon, right? You learn that tertiary carbons are good carbocations and they are also good radicals, right? And because of that, this oxygen is going to pull this electron density even more because it knows it can handle such positive charges because it's a tertiary carbon, right? But from here, this is only a primary carbon, and the oxygen knows that primary carbons can't handle that positive charge as well as a tertiary carbon. So it's only going to be pulling it by a little bit. And because of this large pulling, we have a huge delta positive on this hindered side, but only a small delta positive on the less hindered side. And because of that, we now have the ability to attack it with our chlorine, right? Our chlorine is going to come over here, and then this bond will go up to that oxygen, and then we will form um, this, this, and then the Cl, and then this OH will be right there, right? And then you can see how I put them anti to each other because it happens in the backside. They have to be separate from each other, right? So as you can see, we have this. No need now for a acidic workup because we have our alcohol already, right? So this is, if you want to be technical with it, this is SN1 type, right? In SN1, we protonate our leaving group, or our leaving group leaves first and leaves a positive. This is exactly what we're doing here, but it's also going to happen. This can leave and then it can attack it over here, or what can happen is it's just going to attack it and then it leaves by itself. So it's an SN1 type mechanism, right? Okay. And then now we're done with this chapter. What's next is chapter 10, and I am not going to be making a video on that because I don't think it's as important as these other concepts that you'll see. Um, so I'm sorry, but I just don't think that. So let's see now how you can figure out this synthesis problem, right? So let's go through our synthesis skills that we learned. So I'm looking at this carbon. I'm looking at this molecule. It has 1, 2, 3, 4, 5 carbons. I'm looking at this molecule and I'm seeing 1, 2, 3, 4, 5, 6, 7. So we went from 5 carbons to 7 carbons, right? I know reactions that add on carbon bonds, and that is a Grignard, right? And we're very lucky here that Grignards, if we react this with a Grignard, let's do 1 carbon, right? Because we added 2 carbons. If we do a Grignard and we do an acidic workup, it's going to attack the less hindered side right here, right? So we're left with um, this. Oops. Right? So now we have 1, 2. We have 1, 2, and then it added on here. Oh, this should only be 1, sorry. Like that. So we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, 6, right? We're almost there. And then now this is an OH. And then we can't do, we need to add on one more carbon chain, right? And if we need to add on one more carbon chain, then we need to add on another Grignard, right? But we can't react this with a Grignard because if we react it with a Grignard, it's just going to deprotonate this hydrogen and take it, right? So what else can we do to make this reactable with a Grignard? We can oxidize it using PCC. If that happens, oops, we get this, right? This is called a ketone now. And because of this, let's see if we have our carbons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? So if we have this, now how do we get it up to here? We just need to add this last carbon chain up here, right? So we can use another Grignard and an acidic workup, right? So let's see what we did first. We knew that we had to add on 2 more carbon bonds, which are on different sides, right? We added on this carbon bond and then this carbon bond. We know that epoxides can react with Grignards to form alcohols, which is what we did here. We did it with an acidic workup and a Grignard, right? We form another bond here, 1, 2, 3, 4, 5, 6 from 1, 2, 3, 4, 5. So we added on this carbon bond. And then we now have a secondary carbon, right? 1, 2. Because we have the secondary carbon, we know we have to add on another Grignard. So because of that, we know that Grignards don't work well with alcohols because if a Grignard were to attack this alcohol, it would deprotonate it and take away this H, leaving this alcohol with a negative charge. So that's not going to happen. So we need to oxidize it using PCC or Jones. It doesn't matter which one because it's a secondary. And when that happens, we form this ketone, which, as you know from previous chapters, it works really well with Grignards. And when it does that, it's going to attack it over here, right? And then we have this acidic workup because when that happens, we form this O with a negative, and then it can just grab on one of the oxygens and then, hydrogens, and then form this alcohol, right? So I congratulate you all for making it through 40A. I hope this was able to help you. Um, I know you will all do amazing on the final. I wish you all the best. And I'll always be here. I'm going to be making more of these for 40C. I'm continuing on making them for 40B as well. So please watch them if you have a chance. And yeah, Good luck on your final, and I hope everything goes well.